Okay, so we've done series circuits and we looked at parallel circuits, and now it's time to take a look at what happens when we combine those elements together, so that we might have sections that are parallel, but there's also series sections within that circuit. So there is kind of a sort of art to solving those kind of problems. It's a little bit like algebra. You know, there are rules that you do have to follow, but at the same time, there's a little flexibility. So there's sometimes different ways in which it can be done. And so that's the devil is in the details. You know, what are those subtle things that you can do, that you do have choices for, but then what are the places where you must follow the rules? And so I'm going to try and give you some sort of like general concepts and strategies that are going to help you to navigate this thing. And we'll talk about at the beginning, you know, where do you start? How do you know where to start? That's what we're going to be really focused on in this combination videos. So we'll take two circuits that show both aspects of the parallel and series combined together, and we'll use those same resistors that we used in the series and parallel circuit, and we'll see how the circuits become a little bit different. You know, we had these two extremes with the series circuit, in which we had a very small amount of current, and then in the parallel circuit, we had this huge amount of current and this huge amount of energy that's being dissipated in the circuit. And so you'll see those are kind of the endpoints. In series, you tend to have very low currents, not a lot of energy being dissipated. And in the parallel circuits, you can dissipate huge amounts of energy with large amounts of current that are going through separate branches. And so there are a few general strategies. And one of the things that is super important to do is to make sure to draw the diagrams in different stages. So what ultimately you're going to do is to draw the original diagram that you're trying to solve. You're trying to find something about the voltage or the current or something, an element in the circuit. And so the first thing to do is to draw that circuit and then begin to simplify it. Look for places where you could simplify. Where can you combine resistors together to replace them with a single equivalent resistor so that we can get this thing down to one resistor? And the reason we want to do that is because we already know the rules for how to find the source current once we get this thing down to one resistor. It's the same process as it would be for a series or parallel circuit. If it was pure, we need to get this down to one resistor, and then that resistor we'll use to calculate the current coming from the battery. Once we have that current, that current is going to be essentially the first real piece of information that we'll have about the circuit. Because of course these REQs, they're not real. You know, they're equivalent resistances, and we could replace the circuit with that resistance, but it's not an actual resistor. It is essentially how the combination of resistors becomes a single resistor. And so once we find that source current, that's the first real thing that we found in the circuit. And with that piece of information, you'll be able to start going back through the circuit. And this is the challenging part. I mean, this is where it gets very difficult. You know, this is basically follow the steps. There's a little bit to think about in terms of which resistors do you combine first. But once you get to the current, you really have to kind of step carefully. There's several paths forward. There's more than one way to do it, but at the same time, there's also ways to misidentify properties and then end up with wrong voltages or wrong currents in other parts of the circuit. So ultimately, once we have this guy, we're going to start working our way back through the diagrams. So we have these diagrams that are getting simpler and simpler and simpler. Now we're going to start working our way backwards to work out voltages and currents in different parts of the circuit. And it's definitely a challenge. So again, in order to do that, we're going to look at the same three resistors that we looked at before, the 5, the 10, and the 15, and we'll use the 12-volt battery, and we'll just see how different combinations produce different amounts of total current, total resistance, and then also the individual voltages are going to be considerably different than they were in the pure circuits. So let's move this out of the way. And what I would suggest that you want to do is move to a new sheet of paper in your notebook. We want to use the entire piece of paper to solve this problem. This is going to be example 1. And I'm going to make the diagram about half the width of the page because I want to be able to go back and put labels on here later if I decide to. Okay, so the three resistors, and we're going to have our battery is 12 volts. Our resistor 1, we'll put the 10 ohm here. Let me turn this sideways. We'll make R2 the 5 ohm resistor, and R3 will be the 15 ohm resistor. All right. So as it said, step one, start simplifying the diagram. Now you got to make a choice about who you're going to combine. Now, what you cannot do is combine this guy with this guy or this one with this one. Okay, and the logic behind that is the current that flows through this is not the same as the current that goes through here. The current that went through this one split up, and some went this way and some went this way. And this relationship is going to be very simple. This has more resistance, therefore it will get less current. You know, imagine you had two doors, one door that was wide enough for one person to go through at a time, and another door that was wide enough for three people to go through at the same time. Obviously, that wider door is going to have a larger current of people passing through it. How much larger? Well, 3 times larger, because for every one person that can get through the other door, 3 people can get through this one. Now remember, this is the resistance. It's not measuring how much can get through, it's measuring how difficult it is to get through. So since this path is 3 times more difficult than this path will get 3 times more current than this one. And you'll see that at the end when we finish the solution. So we cannot add, so in other words, in series, I can't say, well, let me add the 10 and the 5, but then what are you going to do with the 10 and the 15? Right? That's going to cause you to double count the 10. And none of that makes any sense because the current that went through here did not go through this resistor. Only a portion of it did. So in a series circuit, you can add 2 resistors in series if there are no other branches that would allow the current to split off. So that whatever current went through this one was the same current, and I don't mean the same value, I mean the same charges that went through this resistor also must go through this one, but that's not going to happen in this case. So what we must do first is to deal with the parallel section over here. I have a single resistor in here. These two are in parallel with each other. I would say the 15 was in parallel with the 5. Therefore, I can go ahead and use the rule for equivalent resistance to work out what is the value of this. So that's 1 over 5 plus 1 over 15. That does actually have a common denominator, which is 15. For this guy, I would need to multiply by 3. So 3 times 5 is 15. 3 times 1 is 3. Plus 1 more from this guy. That tells me that it is 4 over 15. And therefore, the equivalent resistance of this section would be equal to 15 divided by 4. And that is 3.75 ohms. Okay, so now that essentially what I've done is eliminated this section, let me redraw the new circuit now. And let's relabel things. So 12 volts, this guy is 10 ohms, and we have now figured out that this guy is 3.75 ohms. And I'm going to actually put a little arrow over here. The work is going to get a little tricky to see in some instances, and so I just want to make sure that we're really clear where were we going with this. I found the equivalent resistance for the parallel section. Now I am down to a simple series section. This is very frequently the way that it's going to end, is that you eliminate different sections of the circuit until eventually you just have a bunch of individual resistors. So in this case, I would say REQ is equal to 10 plus 3.75 to give me an equivalent resistance of 13.75 ohms. And now I can get rid of these two, and we are at our final drawing. $12 volts, 13.75 ohms. All right, so let's just real quickly, let's take a look at what happened in the other circuits. When we had this as a pure series circuit, we got an equivalent resistance of 30. And now we only have a resistance of 13.3. We found in the parallel circuit, then we did this, we got a resistance of only 2.73. So remember, those are the extremes. The parallel is going to produce the lowest possible resistance, and the series will produce the highest always. Always, parallel produces the lowest resistance, and series produces the highest resistance. Okay, so we got something in between. That kind of makes sense. So the next step then is to figure out, well, what's the current passing through this? That would be that IS would be equal to the voltage of the battery divided by the equivalent resistance. And I just want to really emphasize, this equivalent resistance is not the resistance in the battery. It's the resistance in the rest of the circuit. It's what the battery is facing. It's what's going to determine what current that battery can produce, because regardless of the voltage of the battery, it can only produce as much current as it has the capacity based on the resistance in that circuit. So the REQ is not a property of the battery. The voltage and the current are a property of the battery, but this is a property of the outside circuit. This voltage being applied to this resistance is going to produce this current in the circuit. So that was 12 volts divided by 13.75 to give us a current of 0.87. And let me just tell you what that next number is. 12 divided by 13.75. That is 8.73. And that would be amps. Again, this is the first real property of the circuit, because these equivalent resistors are not real. They don't actually exist. They're just a mathematical tool for us to figure out what's going on in the circuit. So we found we had 0.87 amps. Let's remember what we saw in series. In series, we found that we had a current of 0.4 amps. So we're getting a little more than double the amount of current with the same resistors and the same battery. But in parallel, we got 4.4 amps. So way below what we would have gotten if we'd have put these guys into pure parallel circuits. All right, so now it's time to start going back and working our way through. And this is a little delicate because I'm really looking at all of the diagrams. So here's one thing I notice. If I could figure out this voltage, that would be the same voltage as these parts right here. Because remember, each of these two guys has the same voltage as each other. But in this case, this is really important. In this case, they don't have the voltage of the battery because there was somebody in series. And this person in series is obviously, as the charge comes out, before it can even get to the branch, some of that energy will be used. Some of the energy is going to be gone. So it is simply not available for this part of the circuit. And so whatever the voltage in these two, it's the same. And remember, these two are replaced by this guy. So this diagram is going to allow us to get a lot of information. In fact, we'll basically get almost everything from this diagram, even though remember, this doesn't exist. There is no circuit diagram. There's no circuit like this. It is an imaginary circuit that will produce the same results as the circuit that we have up here. It's an equivalent circuit. So the first thing is, let me calculate these two voltages. So the first one I'm going to do is V1, and that is simply going to be equal to I1 times R1. And so I1 is going to be 0.873 because look, there's no branches. So 0.873 left the battery, and this is what I'm saying was so important about this current. In this diagram, I can tell you the voltages on both of these, and at that point I'll be done. I will have all the voltages for all of the resistors, because remember, this resistance, or this voltage I should say, is the same voltage as we're going to see in this part of the circuit. This guy replaced these guys, so therefore it must have the same voltage as this section of the circuit. So in this case, the I is 0.873, and that is multiplied by 10 to give me a voltage of 8.73 volts. Okay, V2 is equal to V3, and they will be simply equal to also I times R. Now, here's the thing. I'm not going to call it I2 or I3 because it's not I2 or I3. I know the current split up. So the 0.87 went through here, but to get through these two, it had to split up. So I know that's not the current for that guy. So I'm looking at this one. There's only one current through this section. And remember, this section replaced this one, so I can say 0.873 times that resistance, which was 3.75, and that will be equal to, 0.873 times 3.75. That gives me 3.27 volts. Let's add those up. Let's see what those add up to. 8.73 plus 3.27 equals exactly what should have happened, right? These two voltages should have added up to the voltage of the battery, and they did. Okay, but now I know that this voltage, 3.27, is actually the voltage on each of these two guys also. Okay, so the last piece of information that I need is the current I2 and I3. And once I have those, then I will be done. So the question is, we had 0.87 amps. How did that 0.87 amps break up? Well, now I know how to do it. So V2 over R2, V3 over R3. I always had the resistance, but I didn't have the voltages, and now I do. 3.27 divided by resistor 2, which was 5, and 3.27 divided by 15. Okay, 3.27 divided by 5 is equal to 0.654, and 3.27 divided by 15 is equal to 0.218. Let's see what happens if I divide those two. 0.654 divided by 0.218, and I get 3, exactly what we said was going to happen. The current in the lower resistance part of the circuit was 3 times more than the current here. When I add those two together, I get 0.873. Right, so exactly what we would have expected from this circuit.